Hey, my name is Amna, and you are watching Amna Unfiltered. Today we're diving into a topic that's quickly becoming the backbone of innovation in our modern world, AI agents. Now, I know what you're thinking. What exactly is an AI agent, and why should I care? Trust me, by the end of this, you'll see how AI agents are shaping the future in ways that will blow your mind and perhaps even change the way you interact with technology. Let's start with a simple question. Have you ever used a virtual assistant like Siri or Alexa to set a reminder, check the weather, or even turn on your lights? That right there is an AI agent at work. It's a program that listens, learns, and acts on your commands, all while adapting to your preferences to make your life easier. AI agents are the invisible hands behind everything from your music recommendations on Spotify to the bots that help you navigate customer service issues online. But here's where it gets even more fascinating. Imagine a world where these agents are no longer just responding to your commands or queries, but are actively working to optimize processes, anticipate your needs, and make decisions without you lifting a finger. Picture this. You're driving to work, and instead of you worrying about the best route, your car's AI agent already knows about the traffic, adjusts your route in real time, and even suggests the perfect playlist to keep you relaxed. And that's just the beginning. AI agents are transforming industries in ways that were once only dreamed about in science fiction. In healthcare, AI agents are being used to analyze patient data, track symptoms, and even assist doctors in diagnosing diseases. In finance, algorithmic trading bots, AI agents, are making lightning-fast decisions on stock trades, helping investors gain or minimize their risks based on complex market analysis. In logistics, they're optimizing supply chains, ensuring products get to you faster and with less cost. The possibilities are endless, and as technology advances, so do the capabilities of these intelligent agents. Now, let's take a deeper look at how AI agents work. At their core, these agents are built on complex algorithms and machine learning techniques designed to learn from data, make informed decisions, and continually improve their actions. For instance, a customer service chatbot doesn't just follow pre-programmed responses. It learns from every conversation it has, analyzing patterns in customer inquiries, improving its responses, and providing better service as it interacts more. But it's not all about responding to commands. Many AI agents are becoming increasingly proactive. Think of a smart home system. It learns your habits, what time you wake up, when you come home, and when you go to sleep, and adjusts the environment accordingly without you needing to lift a finger. The lighting dims in the evening, the thermostat adjusts to your comfort level, and the coffee machine starts brewing at the perfect time. All because the AI agent knows your schedule and is working in the background to make your life more seamless. Let's talk about autonomy for a moment. AI agents, especially those in robotics, are becoming capable of operating independently. For example, autonomous vehicles, which are powered by AI agents, are now able to drive themselves, reacting to real-time conditions like traffic, road signs, pedestrians, and other vehicles. They learn from their surroundings, continuously improving their driving strategies, ensuring safety while adapting to various conditions, like inclement weather or busy city streets. This autonomy is a big part of what sets AI agents apart from traditional technology. They don't just follow static instructions. They learn, adapt, and evolve. Of course, there's a balance. While AI agents are designed to make our lives easier, there are also concerns about their growing influence, especially in sectors like employment, security, and ethics. If AI agents can autonomously make decisions, who holds them accountable? How do we ensure that these agents don't unintentionally perpetuate biases or make unethical choices? These are important questions we need to grapple with as AI becomes an increasingly integral part of our daily lives. It's a conversation that goes beyond the technology itself and dives into how we as a society shape its role in the future. So what does all of this mean for you, the viewer? Whether you realize it or not, AI agents are already becoming part of your life, making everyday tasks more efficient, personalized, and manageable. As you interact with your devices, whether it's a smartphone, a voice assistant, or even your car, you're engaging with AI agents that are learning from your behavior, adapting to your preferences, and constantly improving the way they serve you. We're on the cusp of a revolution where AI agents aren't just tools. They're becoming partners in our personal and professional lives, anticipating our needs, solving problems we didn't know we had, and driving forward the next wave of technological innovation. In the next few years, you'll see AI agents in ways you never imagined, making critical decisions in healthcare, driving businesses to new levels of productivity, and even helping to solve some of the world's most pressing challenges, from climate change to poverty. This is not science fiction. This is the reality we're living in, and the role of AI agents in shaping our future is only going to expand. They're not just here to assist, they're here to redefine what's possible, what's efficient, and what's effective. Deep learning, advanced algorithms, and the constant evolution of these intelligent systems are leading us into an era where the future is filled with possibilities, and AI agents are the driving force. So, stick with me as we explore the ins and outs of AI agents, the amazing ways they're transforming industries, and the exciting potential they hold. Together, we'll dive deeper into how these digital assistants are not only changing how we interact with technology, but how they are transforming the world around us. Welcome to the world of AI agents, where the future is now, and it's smarter than ever before. Definition. An AI agent is an autonomous entity that interacts with its environment, processes the information it gathers, and takes actions to achieve specific goals. Yet, this simple definition encapsulates an intricate web of technologies, theories, and real-world applications. To truly understand the essence of an AI agent, we must delve into the core principles of autonomy, perception, decision-making, and goal achievement, all of which intertwine to form the backbone of what makes an AI agent not only a tool, but a dynamic, self-improving entity, capable of navigating its surroundings and executing tasks with a remarkable degree of independence. At the heart of the concept of an AI agent lies its autonomy. In a world dominated by human interaction and control, autonomy means that the AI agent is not reliant on continuous human input to perform its tasks. Instead, it can operate independently, making decisions and taking actions without the need for constant oversight. This autonomy is powered by a robust set of algorithms and learning models that allow the agent to process information, learn from its experiences, and adapt to new situations. The agent does not merely follow a rigid set of instructions. In essence, an AI agent has the freedom to act on its own accord, drawing upon its internal knowledge and decision-making processes to achieve its assigned objectives. The second critical component in the framework of an AI agent is its ability to perceive its environment. Just as humans rely on their senses, sight, hearing, touch, and more, AI agents perceive their surroundings through sensors. These sensors might be physical devices, such as cameras, microphones, or motion detectors, or they might be digital sensors that collect data from the online world. This perception is what enables the AI agent to understand its context and gather the information necessary for its operations. For instance, a robot moving through a factory uses its sensors to detect obstacles, temperature fluctuations, or variations in its surroundings, all of which feed into its decision-making process. However, perception is more than just collecting raw data. It involves processing and interpreting that data in meaningful ways. An AI agent's sensors feed information into its cognitive framework, where it is analyzed, understood, and translated into actionable knowledge. A sensor might detect a change in the environment, such as a temperature rise in a particular area of a warehouse. The AI agent doesn't just acknowledge this change, but interprets it to determine whether it's a sign of a malfunction, a potential safety hazard, or a necessary operational adjustment. The agent processes data from multiple sensors simultaneously, integrates that information, and forms a cohesive understanding of its environment. It is through this perception that the AI agent is able to interact effectively and purposefully within its environment. With this information at hand, the next step for an AI agent is decision-making, the core of how it acts upon the world around it. After gathering data from its senses, the AI agent must process this information, weigh its options, and make a decision that leads toward the achievement of its goal. This is where the power of machine learning and deep learning algorithms truly shine, allowing the AI agent to take in vast quantities of data and determine the most optimal course of action based on previous experiences or predefined rules. Whether it is a robot navigating a room, a virtual assistant responding to a user's query, or an autonomous vehicle choosing the best route, the agent must make decisions in real time, sometimes with limited or imperfect information. Decision-making is complex and layered. An AI agent doesn't just blindly execute actions, but evaluates potential outcomes, anticipates future states, and adjusts accordingly. If the AI agent is a self-driving car, its decision-making process must take into account countless variables: other cars on the road, pedestrian movements, traffic signals, weather conditions, and road quality. The decision-making process must be both fast and accurate, with the agent calculating not just the immediate best move, but also considering the broader context of the journey. Yet, decision-making in AI agents is not always about choosing the most immediate or obvious option. Often, an AI agent must weigh long-term goals and consider trade-offs, much like a chess player strategizing several moves ahead. A common example of this is seen in reinforcement learning, where an agent learns from its actions through trial and error, receiving rewards or penalties based on its behavior. Over time, the agent refines its decision-making process, continually improving its performance by learning from the consequences of its actions. Achieving goals is the final and most essential aspect of an AI agent's purpose. An AI agent exists for one primary reason: to accomplish a specific task or set of tasks. These goals are usually predefined by the designers or users, but the agent may be tasked with autonomously determining the best path to reach these goals. Whether it's optimizing a manufacturing process, managing an investment portfolio, or simply answering a user's query, the AI agent is programmed to pursue these objectives relentlessly. It doesn't stop until it has completed its task or found an optimal solution. Goal achievement involves not only taking actions, but also evaluating progress. AI agents continuously monitor their performance, adjust their approach, and reorient their actions to stay on track toward their goal. A navigation robot, for example, constantly checks its location in relation to its destination, recalculating the best route if it encounters an obstacle. The AI agent must assess whether the actions it has taken are getting closer to its objective, and if not, revise its strategy accordingly. What makes this process so powerful is the adaptability of AI agents. In a traditional system, a machine might follow a fixed sequence of steps or rules to accomplish a task, but an AI agent has the capacity to learn, adapt, and improve over time. If an AI agent is tasked with inventory management in a warehouse, for example, it might initially perform the task by following a set of basic rules about where products are stored. Over time, however, the agent learns from the data it receives, such as customer purchasing trends or inventory turnover rates, and starts to optimize stock placement, streamlining the process, and improving efficiency. The real magic of AI agents lies in their ability to evolve. As they encounter new environments, data, and situations, they learn from these experiences and adapt their behaviors accordingly. This continual learning process allows AI agents to perform tasks they may not have been explicitly programmed for, creating an unprecedented level of flexibility. Instead of being constrained to rigid functions, AI agents become versatile, capable of handling increasingly complex, unforeseen challenges. One of the key benefits of this adaptability is its scalability. Whether it's an AI agent working in a small warehouse or managing logistics across a global network, the principles of autonomy, perception, decision-making, and goal achievement apply across a wide range of tasks. AI agents can handle large volumes of data, optimize complex systems, and continually improve their own operations, all while remaining efficient and reliable. However, with this incredible potential comes a responsibility to manage AI agents with care. The decisions made by AI agents, whether in healthcare, finance, or transportation, can have far-reaching consequences, especially when dealing with critical systems or sensitive data. It is crucial that these agents operate ethically and transparently, with safeguards in place to ensure they function within set boundaries and align with human values. In conclusion, an AI agent is a multifaceted autonomous entity that interacts with its environment, processes information, and takes actions to achieve specific goals. Through the integration of perception, decision-making, and goal achievement, AI agents are transforming industries, enhancing productivity, and opening up new possibilities for innovation. As technology evolves, these agents will continue to improve, becoming more intelligent, adaptable, and capable of achieving increasingly complex tasks, ultimately making a profound impact on the way we live and work. Autonomy. Autonomy in the realm of artificial intelligence is the very essence that distinguishes an AI agent from other technological tools. It is the core characteristic that allows AI systems to act independently, with little to no direct human intervention, and to achieve objectives through their own decision-making processes. This remarkable ability to perceive, process, and act upon information makes AI agents not just reactive systems, but intelligent, proactive ones, capable of navigating complex environments and solving problems on their own. As we delve into the power of autonomy, we can begin to understand how this principle underpins everything from autonomous vehicles to smart assistants, shaping the future of technology and its interaction with the world. Imagine a world where machines can not only perform tasks, but learn and adapt as they do. Autonomy allows an AI agent to make decisions based on its surroundings and the goals it is programmed to achieve without requiring constant human guidance. Take, for instance, the autonomous car that moves through the streets of a busy city. This car doesn't need a human driver to steer it, navigate traffic, or make decisions about when to stop, go, or turn. Instead, it processes information from cameras, sensors, and mapping systems, all while adapting to real-time traffic data, road conditions, and potential obstacles. The car is able to evaluate its environment, analyze the situation, and act accordingly, all based on its autonomous decision-making system. This capacity to perceive and act independently is what makes it an AI agent, a system that doesn't just respond to external stimuli, but also makes decisions based on its goals and understanding of the world around it. Autonomy in AI is fundamentally tied to the idea of an agent as a self-directed system. Just like a human being doesn't need to be constantly told how to perform basic tasks, an autonomous AI agent operates with a level of independence that allows it to function in real-world environments without needing continuous input. Consider the example of a robot working in a warehouse. This robot is equipped with sensors that allow it to perceive its environment, from detecting obstacles to identifying where specific products are located. It processes the information it gathers and makes decisions on how to move through the space, pick up items, and deliver them to the correct location, all without requiring a supervisor to tell it what to do next. Over time, as it interacts with the environment, the robot may also learn more efficient ways to perform its tasks, further enhancing its autonomy. The autonomy of AI agents is powered by sophisticated algorithms and models that allow them to process data and make decisions without direct human input. These algorithms can range from simple decision trees, where the system follows a set of predetermined rules, to complex deep learning models that mimic human brain processes and are capable of learning from vast amounts of data. At its core, autonomy in AI is about creating systems that can operate in dynamic, unpredictable environments while continually adjusting their behavior to meet goals and objectives. This level of independence is not confined to physical robots or autonomous vehicles. In the realm of software, we see autonomous AI agents making decisions in real time to optimize business processes, drive personalized user experiences, and even perform highly specialized tasks. Take, for example, an AI power-powered recommendation engine on an e-commerce website. Based on the actions of the user, the system autonomously analyzes purchase history, browsing behavior, and even social media activity to offer product suggestions tailored to the individual. This recommendation engine doesn't rely on constant updates from human programmers. It processes information on its own, continuously improving its suggestions as it learns more about the user's preferences. The result is an experience that feels seamless and intuitive, all powered by the autonomous capabilities of AI. In more complex systems, autonomy allows AI agents to take on tasks that were once the sole domain of human workers. In financial trading, algorithmic trading systems are autonomous agents that monitor market conditions, execute trades, and adjust strategies based on real-time market data. These systems are designed to work independently of human traders, making decisions in fractions of a second based on vast amounts of data that no human could possibly process in real time. The AI agents can respond to market shifts, detect trends, and execute trades with incredible precision, improving efficiency and profitability. In industries like healthcare, autonomous AI agents are beginning to take on roles such as analyzing medical images, diagnosing diseases, and even recommending treatments based on patient data. These systems autonomously process vast amounts of medical information, offering insights that can aid doctors in making more accurate, timely decisions, while also helping to reduce the strain on healthcare professionals. But autonomy is not without its challenges. While AI agents are capable of making decisions and acting independently, these systems are only as good as the data and algorithms that power them. Biases in data or flawed decision-making models can lead to undesirable or harmful outcomes. Consider a case where an AI-powered hiring system is designed to autonomously screen job applications. If the system is trained on historical data that reflects biases, such as underrepresentation of certain demographics or gender disparities, the system could perpetuate these biases, leading to unfair hiring practices. Similarly, the autonomy of AI systems in sensitive areas like criminal justice or healthcare requires robust ethical frameworks to ensure fairness, accountability, and transparency in their decision-making processes. As we look to the future, the demand for AI agents with greater autonomy is only expected to grow. From smart homes that learn and adapt to your lifestyle, to industrial robots that work alongside human workers, the scope of autonomous AI applications is vast. However, as these systems become more integrated into our daily lives and decision-making processes, it becomes increasingly important to ensure that the technology remains transparent, understandable, and controllable, ensuring that AI systems operate within ethical boundaries, respect human rights, and provide mechanisms for oversight is crucial as we move towards a more autonomous future. At the same time, autonomy in AI also opens the door for more collaborative forms of human-machine interaction. Far from replacing humans, autonomous AI agents are increasingly seen as partners that augment human capabilities, offering solutions to problems that were once too complex or time-consuming for individuals or organizations to tackle alone. The true power of autonomy lies not in the isolation of AI agents, but in their ability to work alongside humans, complementing human strengths with machine efficiency and precision. In conclusion, autonomy is the cornerstone that makes AI agents transformative. The ability to perceive, process, and act independently enables AI systems to perform tasks, make decisions, and improve over time with minimal human intervention. From self-driving cars to personalized recommendations, autonomous AI agents are reshaping industries and revolutionizing how we interact with technology. While there are challenges to be addressed, particularly in areas of ethics and accountability, the potential of autonomous AI to enhance our lives and solve some of the world's most pressing problems is vast. As AI continues to evolve, its autonomy will unlock new possibilities, enabling us to achieve more, innovate faster, and create a future where humans and machines work together in harmony to solve problems and drive progress. Perception. Perception is the gateway through which AI agents interact with the world, a vital and foundational aspect that empowers them to understand and respond to their surroundings. In the same way that human beings rely on their senses to interpret the environment, seeing, hearing, feeling, and tasting, AI agents too depend on sensors, whether physical or digital, to collect data and form a representation of the world around them. This process is not passive. It involves active interpretation, analysis, and understanding of the information, which in turn shapes the agent's actions. The ability to perceive and make sense of the environment is what allows AI agents to make informed decisions, predict outcomes, and take effective actions based on real-time inputs. At its core, perception in AI agents is about translating raw data into meaningful insights. Imagine a robot moving through a warehouse filled with shelves, boxes, and obstacles. Its sensors gather a continuous stream of information: depth from cameras, temperature from infrared sensors, motion from accelerometers, and each piece of data helps the robot understand its position in space, the objects around it, and the conditions that might affect its movement. Without this perception, the robot would be blind, unable to navigate, identify objects, or even recognize when a task is completed. Instead, through perception, the AI agent can construct an internal model of its environment, allowing it to interact effectively and carry out tasks like picking up boxes, placing them on shelves, or avoiding obstacles. This process begins with sensors, which are the eyes and ears of AI agents. Sensors come in many forms, from cameras and microphones to temperature sensors and GPS devices, each designed to capture a specific type of information from the environment. Cameras, for instance, capture visual data, enabling an AI agent to see the world around it, while microphones record sound, allowing it to hear. Other sensors might detect changes in light, temperature, or pressure, providing further contextual information. In more advanced applications, Sensors might even include biosensors that monitor the health of individuals or environmental conditions, further enhancing the AI agent's ability to understand and respond to its surroundings. Once the AI agent has gathered data through its sensors, the next step is interpretation. This is where the magic happens. Raw data is meaningless unless it is processed and understood. The data gathered by the sensors must be analyzed, and this analysis requires sophisticated algorithms and machine learning models that can recognize patterns, relationships, and anomalies in the data. This process involves breaking down the data into components that the AI can make sense of, much like how the human brain processes visual information into identifiable objects. For example, when a self-driving car's camera captures an image of the road, the AI agent uses algorithms to detect lane markings, identify pedestrians, recognize traffic signs, and understand the flow of traffic. This allows the car to comprehend the state of its environment and make decisions such as when to slow down or stop. In some cases, perception involves more than just recognizing individual elements. It's about understanding how those elements relate to each other within a given context. For example, in the case of a drone flying through a city, it needs to understand not just the obstacles in its path, but also the relationship between those obstacles, such as the distance between buildings and its own position, so that it can adjust its flight path accordingly. The ability to perceive and understand spatial relationships is critical for ensuring that the AI agent can make safe and effective decisions in dynamic environments. But perception is not limited to physical sensors. Digital sensors also play a key role, particularly in fields such as cybersecurity, finance, and social media. In these realms, AI agents gather data from digital sources, social media platforms, financial transactions, or even online customer interactions, and interpret this data to understand trends, behaviors, and potential risks. In cybersecurity, for example, AI agents analyze network traffic, detect patterns of malicious activity, and flag potential threats in real time. These digital sensors don't rely on physical inputs, but instead leverage the vast amounts of information available on the internet to perceive and act upon potential security breaches. Another fascinating aspect of perception is the role of artificial intelligence in processing sensory information over time, continuously learning and refining its ability to understand the environment. This is where machine learning and deep learning come into play. Through exposure to large data sets and experiences, AI agents learn to perceive more accurately, detecting patterns and making decisions based on past data. In essence, the more an AI agent perceives, the better it becomes at understanding its environment. Take the example of a voice assistant, like Siri or Alexa. When these systems first started, they were limited in their ability to understand accents, slang, or complex phrases. However, as they processed more spoken data, their perception capabilities improved, allowing them to more accurately interpret speech, no matter how diverse or nuanced it was. This adaptability, powered by learning, is one of the keys to the effectiveness of AI agents in real-world applications. This capacity for continuous improvement through perception is one of the most powerful attributes of AI agents. For example, in the context of autonomous vehicles, an AI agent can continuously learn from its environment, improving its ability to navigate streets, avoid hazards, and make safe driving decisions. With every mile driven, the AI agent perceives new patterns in traffic flow, pedestrian behavior, and road conditions, which allow it to become better at predicting outcomes and reacting to unforeseen events. This ongoing process of perception and learning is one of the reasons why AI agents, especially those operating in dynamic environments, can operate at a level of efficiency and adaptability that traditional systems simply cannot match. The importance of perception in AI agents extends far beyond autonomous driving, robotics, or virtual assistants. In healthcare, perception plays a crucial role in diagnostic systems that analyze medical images. AI agents equipped with deep learning algorithms can perceive minute changes in XRIs or MRIs or CT scans that human doctors might miss. This capability enables early detection of diseases like cancer, which can be vital for successful treatment. By accurately interpreting visual data from medical scans, AI agents not only assist in diagnosis, but also improve the speed and accuracy of the healthcare process, allowing doctors to focus on treatment while AI handles the intricate task of perception and analysis. In retail, perception is crucial for understanding customer behavior. AI agents can track customers' actions in physical stores or on e-commerce websites, interpreting these behaviors to offer personalized recommendations, promotions, or advertisements. By perceiving patterns in shopping habits, AI agents can predict what products customers are likely to purchase next, enhancing the shopping experience and increasing sales for businesses. Yet, with all the remarkable capabilities of AI agents, there are challenges in perfecting perception. One of the key difficulties lies in the quality of data that these agents rely on. If the data is noisy, incomplete, or biased, the agent's ability to perceive the environment accurately can be compromised. A self-driving car, for example, could misinterpret a road sign or fail to identify a pedestrian due to sensor malfunctions or poor weather conditions. This highlights the need for robust and diverse training datasets, as well as continuous monitoring and updates to ensure that AI agents can perceive their surroundings accurately, even in the most challenging conditions. Action. Action is the culminating step in the intricate journey of an AI agent's interaction with its environment. It is the moment when perception and processing meet decision-making and take tangible form in the real world, whether through a subtle notification or a complex, multi-step task that requires precise execution. This process of translating the information gathered and analyzed into effective actions is what makes AI agents not only powerful, but transformative, enabling them to engage meaningfully with their surroundings, solve problems, and even predict future needs. The ability of AI agents to act autonomously is what sets them apart from traditional systems, empowering them to perform a wide variety of tasks that were once thought to require human intervention. Imagine you're using a virtual assistant like Siri or Alexa, and you ask it to remind you of an appointment in an hour. The AI agent perceives your request through speech recognition, processes it, and then takes action by setting a reminder on your device. This simple action, though seemingly trivial, is the result of a series of complex processes. The AI agent has to recognize the intent behind your request, retrieve and store relevant data, in this case, the time of the appointment, and then execute the reminder function at the designated time. This is a relatively simple task, but it underscores a key principle. AI agents act based on processed data to fulfill a specific function or goal. But the scope of action in AI is not limited to such basic functions. In many cases, AI agents are called upon to execute highly intricate tasks that require a level of coordination, real-time decision-making, and adaptability. Take the example of an autonomous vehicle navigating through busy city streets. The AI agent in this context continuously processes data from sensors, cameras, radar, and LiDAR to create a comprehensive map of its environment. It must interpret traffic signals, pedestrians, other vehicles, road signs, and environmental conditions, and then perform actions based on this data, such as adjusting speed, turning, or stopping. These actions must be executed with an incredible degree of precision and timing to ensure safety and efficiency. And they must be done in real time, responding to changes in the environment without delay. For this level of autonomy, AI agents need to be able to not only perform tasks in the moment, but also anticipate and plan for actions ahead of time. Take, for example, a robot working in a manufacturing facility. The robot must not only execute tasks like picking up and placing parts, but also plan its movements to avoid collisions, optimize its path, and adjust based on the changing layout of the workspace or the actions of nearby robots and humans. The robot's actions are a result of both immediate decision-making and a long-term strategy, a combination of reactive and proactive measures that ensure the task is completed efficiently and without errors. The complexity of actions AI agents can perform only increases when multiple tasks or systems are involved. In industries like logistics or supply chain management, AI agents are responsible for optimizing the flow of goods, monitoring inventory levels, and making decisions about restocking or rerouting shipments. These tasks involve gathering data from different sources, warehouse sensors, delivery tracking, market demand signals, and performing actions like reordering stock, shifting inventory, or alerting managers to potential supply shortages. In each instance, the AI agent must process vast amounts of information, make decisions that balance cost, time, and resources, and then take coordinated action to execute those decisions seamlessly across the network. In healthcare, AI agents are being utilized to act as critical decision-making support tools, particularly in complex diagnostic or treatment processes. Consider the role of AI in analyzing medical images like MRIs or X-rays. The AI agent scans through high-resolution images, processes the data to detect signs of diseases such as tumors, fractures, or early indicators of neurological conditions, and then takes action by flagging these abnormalities for further review by doctors. The action here is not just flagging a potential issue, it's a call to attention, ensuring that the healthcare professional can focus on the most important findings and make informed decisions about patient care. In the realm of customer service, AI agents are transforming the way businesses interact with their customers. Automated chatbots are tasked with addressing customer inquiries in real time, analyzing the content of the customer's message, determining the intent, and responding with the most appropriate action. These actions range from providing answers to common questions, escalating more complex issues, to human agents, or even suggesting relevant products or services. As these AI agents learn from their interactions, their actions become increasingly accurate, personalized, and capable of managing even more complex customer service tasks. Even in fields like cybersecurity, where AI agents play an increasingly vital role, their actions can be highly sophisticated. These agents constantly monitor networks for any signs of security breaches or irregular activity. Upon detecting potential threats, they take action by automatically blocking suspicious traffic, alerting system administrators, or even initiating corrective measures to neutralize the threat before it can escalate. In these environments, the AI agent's ability to act swiftly and accurately can make the difference between preventing a major security incident or letting it spiral out of control. The ability of AI agents to perform actions in real time is crucial in today's fast-paced, interconnected world. Consider the importance of real-time action in financial trading. Algorithmic trading systems use AI agents to scan the market, process millions of data points, and execute trades in fractions of a second. These agents not only act on current market conditions, but also anticipate future trends based on historical data, making split-second decisions that can capitalize on fleeting opportunities. These high-frequency trading systems rely on AI agents that perform actions with lightning speed and without human oversight, allowing investors to profit from even the smallest shifts in market behavior. Yet, the nature of AI agent actions isn't solely limited to traditional business functions. In the field of artificial intelligence, the concept of action is also about improving the intelligence of the system itself. Deep learning models, for example, can act by making adjustments to their internal processes after being exposed to new data. As an AI agent is exposed to new information, it may alter the way it perceives its environment, changing its responses or refining its predictions. This ability to improve and adjust based on feedback is one of the key elements that distinguishes intelligent systems from traditional rule-based systems. The breadth and diversity of actions performed by AI agents highlight their potential to revolutionize numerous industries, from healthcare and finance to entertainment and logistics. However, the power of action in AI also comes with a responsibility. Ethical concerns are increasingly raised as AI systems take on more decision-making responsibilities. How can we ensure that the actions of AI agents are aligned with human values and ethical standards? How can we prevent AI agents from making harmful or biased decisions, particularly in sensitive areas like hiring, law enforcement, or healthcare? The actions of AI agents must be transparent, explainable, and accountable to avoid unintended consequences and ensure that their power is harnessed responsibly. Looking to the future, the ability of AI agents to take action will only continue to evolve and expand. As they become more integrated into the fabric of everyday life, their ability to perform increasingly complex tasks autonomously will redefine industries, redefine workflows, and redefine human interaction with technology. From autonomous vehicles that navigate our cities with precision, to AI-during personal assistants that manage our homes and schedules, to robots that collaborate with humans on manufacturing floors, AI agents will not just be tools, they will be co-creators in the new digital age. In conclusion, the action performed by AI agents is the manifestation of their intelligence, their ability to not only process information but also to act upon it in a way that creates value, solves problems, and improves the world around us. These actions are the culmination of perception and decision-making, translating thought into reality with precision, speed, and adaptability. As AI agents continue to learn and grow, their capacity to take effective action will shape the future of automation. Business, healthcare, transportation, and countless other fields, marking the dawn of an era where machines do more than assist. They actively drive progress and innovation. Learning is the very essence of what makes AI agents so powerful and adaptable, setting them apart from traditional rule-based systems. The ability of AI agents to learn from their experiences and interactions allows them to continually improve, making them more efficient, accurate, and insightful over time. This process of learning, whether through machine learning, reinforcement learning, or other methodologies, empowers AI agents to not only perform tasks, but to evolve, adapt, and solve problems in ways that were once the exclusive domain of human intelligence. At the heart of AI learning is the concept of data. Just as humans learn from experiences, observations, and interactions with the world around them, AI agents learn from the vast amounts of data they process. This data can take many forms, ranging from structured data sets to unstructured information, such as images, text, and audio. By analyzing this data, AI agents are able to detect patterns, make predictions, and take actions that are based on learned knowledge. With every new piece of data, the AI agent refines its understanding of its environment, improving its ability to make decisions and perform tasks. The process of machine learning, the primary method through which AI agents learn, is a dynamic ongoing cycle that starts with data and evolves through iterative training. In traditional machine learning, an AI agent is exposed to a large data set that contains examples of the desired behavior or outcome. The system processes this data and adjusts its internal parameters to minimize errors and improve predictions. For example, a machine learning model designed to identify objects in images is trained on thousands of labeled images, gradually learning to recognize patterns such as shapes, colors, and textures that correspond to different objects. Over time, the model becomes more accurate, learning from each image it processes, improving its ability to correctly identify new, unseen images. The beauty of machine learning lies in its ability to improve automatically without needing explicit programming for every possible scenario. Unlike traditional systems where rules are hard-coded by humans, machine learning models adjust based on the patterns they detect in the data, allowing AI agents to handle an enormous variety of tasks without being specifically programmed for each one. This autonomy and flexibility is what enables AI agents to perform a wide array of functions, from predicting stock market trends to recommending products to customers on an e-commerce platform. A key characteristic of machine learning is its ability to generalize from the data it processes. When an AI agent learns from examples, it doesn't simply memorize the data. It learns the underlying patterns that govern that data. This means that once the model is trained, it can apply its learning to new, unseen examples, making predictions or taking actions even when faced with situations it hasn't encountered before. For instance, an AI system trained to recognize animals in images can eventually identify new animals that were not part of the original training data, as long as those new animals share certain features with the examples it learned from. However, learning is not always a straightforward process. It involves numerous challenges, particularly in cases where the data is noisy, incomplete, or biased. When an AI agent is trained on imperfect data, it can learn incorrect patterns or make flawed decisions, which could have serious consequences. To mitigate this risk, it is crucial to ensure the quality and diversity of the data the AI agent is trained on. A data set that is too narrow or not representative of real-world situations may result in an AI agent that performs well under specific conditions, but fails when confronted with unexpected scenarios. To address this, techniques like data augmentation, cross-segregation, and regression are used to ensure that the learning process is robust and adaptable to different situations. Reinforcement learning, RLL, another powerful approach to AI learning, takes this concept of learning from experience to an entirely new level. Unlike traditional machine learning, where the system is trained on labeled data, reinforcement learning allows AI agents to learn through trial and error, receiving feedback from their actions and adjusting their behavior accordingly. In reinforcement learning, an AI agent operates in an environment, takes actions, and receives rewards or penalties based on those actions. Over time, the agent learns to maximize its rewards by choosing actions that lead to the best outcomes, effectively teaching itself how to achieve its goals through experience. Consider the example of a robot learning to navigate a maze. At first, it has no idea how to reach the exit, and each action it takes, whether it turns left or right, might lead to an obstacle or dead end. However, when it takes a correct action, such as turning toward the exit, it receives a reward, reinforcing the behavior. Over time, the robot learns to navigate the maze more efficiently, gradually improving its ability to find the exit based on the cumulative feedback it receives. This process mirrors how humans learn from experience, making reinforcement learning particularly powerful in situations where explicit instruction or supervision is not available. The application of reinforcement learning is seen across many domains. In robotics, it enables machines to perform tasks that require decision-making and adaptation to changing environments. In gaming, reinforcement learning algorithms are used to train AI agents to play and excel in games, even defeating human champions in complex games like Go or Dota 2. The ability of reinforcement learning to enable AI agents to optimize their strategies through experience rather than relying solely on predetermined rules has opened up a world of possibilities for autonomous systems capable of learning and adapting in real time. The learning process of AI agents is not just about improving individual tasks. It extends to learning how to interact with humans, communicate effectively, and collaborate in ways that enhance human capabilities. In the case of virtual assistants or customer service bots, the learning is centered on natural language processing, NLP, where AI agents learn to understand and respond to human language. Through repeated interactions, the AI learns to improve its responses, adjusting to various dialects, accents, and cultural contexts, ultimately providing a more seamless and personalized experience for users. Another crucial aspect of AI learning is its ability to continually adapt to changing conditions. The world is constantly evolving, and so are the environments in which AI agents operate. For example, in the realm of autonomous vehicles, the AI agent must not only navigate in real time, but must continuously adjust its learning model based on new traffic patterns, road conditions, or even changes in weather. This adaptability is a hallmark of modern AI systems, allowing them to respond to shifts in their environment and perform optimally in an ever-changing world. Goal-oriented AI agents are, at their core, goal-oriented entities, programmed to achieve specific objectives or perform distinct tasks, acting as agents of transformation in almost every domain they inhabit. This focus on goal achievement is what makes AI so uniquely valuable. Unlike traditional automation tools that may simply execute predefined actions, AI agents are designed with a specific purpose in mind, allowing them to autonomously adapt and continuously refine their approach to reach their goals. Whether it's optimizing processes, responding to queries, or performing autonomous operations, the goal orientation of AI agents defines their effectiveness and relevance in modern technology. Think about the role of an AI agent in a business setting, where its sole purpose is to streamline operations and enhance efficiency. For example, in manufacturing, an AI agent could be tasked with optimizing the production line. Through the integration of sensors, data collection, and real-time analysis, the agent monitors various parameters like machine performance, inventory levels, and throughput rates. Based on these inputs, the AI agent is capable of making real-time decisions, adjusting the production schedule, ordering raw materials when supplies are low, or even predicting equipment failures before they occur. In this scenario, the goal is not just to keep things running, it's to ensure that the entire operation runs smoothly, efficiently, and at its maximum capacity with minimal waste and downtime. This goal-oriented behavior is made possible by the algorithms and data models that underpin the AI agent's design. These models allow the agent to prioritize objectives, make decisions that align with those goals, and optimize its behavior over time. In this sense, the goals of AI agents serve as a guiding compass, helping them navigate complex tasks and challenges with remarkable accuracy and efficiency. For instance, an AI agent responsible for route optimization in a logistics company might aim to reduce delivery times while minimizing fuel consumption. By analyzing historical traffic data, weather forecasts, and delivery schedules, the agent continually adjusts routes and schedules to meet the overarching goal of timely, cost-convertible deliveries. Goal-oriented AI systems also excel in dynamic environments where conditions are constantly changing. A self-driving car, for example, is an AI agent designed to navigate the road safely. Its primary goal is to reach its destination without incident, but the car must constantly adapt to new information, such as traffic patterns, road closures, or obstacles in the path. It processes data from sensors and cameras, makes decisions in real time, and continuously adjusts its actions to meet the ultimate goal of delivering passengers to their destination safely. The car doesn't just react to immediate threats, it proactively adjusts its driving strategy, whether that means slowing down in a construction zone or finding an alternate route when faced with heavy traffic. In customer service, AI agents like chatbots or virtual assistants are programmed to address customer queries, solve problems, and provide assistance across various platforms. Their goal is clear: to resolve customer issues as efficiently as possible, creating a seamless user experience. However, these AI agents go beyond simply providing pre-written answers. They continuously learn from interactions, adapt their responses, and improve their problem-solving abilities based on the complexity and variety of customer inquiries. By maintaining this focus on their goal, resolving issues in a user-friendly manner, AI agents can handle everything from basic inquiries to more complex tasks, such as processing refunds or troubleshooting technical problems, all while providing users with an increasingly refined experience over time. The flexibility and adaptability of goal-oriented AI agents are key to their success. For example, AI-powered recommendation engines used in e-commerce platforms are another example of how goal orientation drives these agents. Their goal is to provide customers with personalized product suggestions, improving the shopping experience and driving sales. By analyzing past purchasing behavior, browsing habits, and even customer reviews, AI agents continually refine their recommendations to offer products that align with the unique preferences of each individual customer. As customers continue to interact with the system, the AI agent learns and adapts, ensuring that the recommendations are ever more relevant, personalized, and timely. This constant adaptation is what sets AI agents apart from simpler algorithms or static systems, as they are continuously striving toward the goal of optimizing the customer's shopping experience. In more advanced applications, AI agents are tasked with solving complex, long-term goals that require multi-step planning and decision-making. For instance, in the field of healthcare, AI agents are increasingly being used to analyze medical data, assist with diagnostics, and recommend treatment plans. These AI agents are goal-oriented in that their overarching objective is to improve patient outcomes. However, achieving this goal requires a series of intermediate tasks, such as interpreting medical images, reviewing patient histories, comparing various treatment options, and even coordinating with medical professionals to ensure that care is provided in the most effective way possible. The AI agent must not only make accurate decisions in real time, but also evaluate and predict long-term outcomes, factoring in various possible treatment paths and the potential impacts on the patient's health. What makes goal-oriented AI agents even more powerful is their ability to perform tasks autonomously. In many cases, these agents do not require constant human input to achieve their goals. Instead, they operate based on their internal models and algorithms, which allow them to make decisions, adjust their actions, and monitor progress independently. This autonomy opens up new possibilities in fields where human labor is limited or where continuous monitoring and adaptation are needed. In agriculture, for example, autonomous AI agents are being used to monitor soil conditions, adjust irrigation levels, and even harvest crops. These agents are goal-driven, with the ultimate objective of optimizing crop yield and reducing waste. Yet they make adjustments on their own, based on real-time environmental data. However, the complexity of goal-oriented AI agents also means that they must have a robust framework for decision-making. This often involves incorporating multiple layers of decision rules, heuristics, or even deep learning models that help the agent prioritize tasks and decide which actions are most likely to achieve its goal. This is especially true in environments where there are competing goals or trade-offs that need to be balanced. For example, in supply chain management, the goal of minimizing costs might conflict with the goal of ensuring that customers receive their orders as quickly as possible. In this case, the AI agent must weigh the importance of these competing goals and take action in a way that balances both objectives. The learning aspect of AI agents further enhances their ability to pursue goals. Over time, an AI agent can improve its performance by learning from its experiences. In the case of a recommendation system, the AI agent can refine its suggestions based on customer feedback and purchasing behavior, constantly adapting its approach to better serve the goal of increasing customer satisfaction and driving sales. In an autonomous vehicle, the agent can learn from past driving experiences to improve its ability to navigate roads, avoid accidents, and respond to changes in traffic conditions. This process of learning from feedback, continuously adjusting actions, and improving performance over time is what allows AI agents to evolve and become more effective at achieving their goals. In conclusion, goal-oriented AI agents represent a breakthrough in technology, allowing machines to not only perform tasks, but to think and act strategically towards specific objectives. Whether it's optimizing processes in business, making real-time decisions in healthcare, or enhancing user experiences in retail, these AI agents are transforming industries, improving efficiency, and solving problems with unprecedented levels of accuracy and autonomy. The ability to continually learn, adapt, and improve ensures that AI agents remain at the cutting edge of technological progress, driving innovation and paving the way for a future where intelligent systems are seamlessly integrated into every aspect of our lives. Decision-making. Decision-making in AI agents is a powerful and foundational aspect of their design, enabling them to make choices that are not just reactive but proactive, informed, and in many cases optimized for the best possible outcome. The ability of AI agents to make decisions autonomously allows them to perform a wide array of tasks, from the simple such as predicting financial market trends or autonomously driving a car. At the core of this decision-making ability is the underlying algorithms that drive AI behavior. Algorithms that must consider the current state of the agent's knowledge, the data it has access to, and the desired goals it is programmed to achieve. These algorithms come in many shapes and sizes, including rule-based model systems, neural networks, and probabilistic models, each of which plays a unique role in how an AI agent assesses its environment and selects an appropriate course of action. The first layer of decision-making, and perhaps the most intuitive, is the rule-based system. These systems rely on predefined rules that dictate what actions an AI agent should take based on specific inputs. A rule-based system operates on an if-then basis, where the agent checks certain conditions and responds accordingly. For example, in a customer service chatbot, if a user asks a question about store hours, the chatbot might look for the keyword hours and then respond with the appropriate answer. While rule-based systems are efficient for straightforward, deterministic tasks, they can be quite limited in their scope. They are not designed to learn from new information or adapt their responses based on complex, variable input. They simply follow the rules they have been given. This makes them ideal for situations where the tasks are well-defined and the environment is relatively static, but less effective in dynamic, unpredictable scenarios. Enter neural networks, a more sophisticated approach that represents a major leap in decision-making capabilities for AI agents. Neural networks are inspired by the structure of the human brain, and just as our brains consist of billions of interconnected neurons, a neural network is made up of layers of artificial neurons that work together to process information. These networks excel at handling more complex and nuanced data, such as images, sound, and unstructured text. The power of neural networks lies in their ability to learn from data, which makes them incredibly effective for tasks that involve pattern recognition. For instance, in image classification, a neural network can learn to distinguish between different objects by processing thousands or even millions of labeled images. Over time, the network adjusts its internal parameters based on the feedback it receives, improving its decision-making process to the point where it can identify new images with remarkable accuracy. A neural network-based decision-making system doesn't simply react to data, it learns from it, adapting its decision-making process over time. This ability to continuously improve is what makes deep learning, a subset of machine learning, so powerful. In real-time applications, neural networks can refine their strategies based on the incoming data, adjusting their actions to meet changing conditions. For example, in self-driving cars, the neural network processes vast amounts of sensor data from cameras and radar to understand the car's environment. As the system encounters different road conditions, obstacles, and traffic patterns, it learns to make better decisions on how to navigate and drive safely, constantly adapting its behavior based on past experiences. Unlike rule-based systems, which rely on rigid rules and predefined scenarios, neural networks can process vast amounts of real-world data and make decisions that were never explicitly coded into the system. While rule-based systems and neural networks are incredibly powerful, they are not always sufficient on their own, especially when the environment is uncertain or when decisions need to be made in situations of ambiguity. This is where probabilistic models, such as Bayesian networks and Markov decision processes, come into play. Probabilistic models allow AI agents to make decisions based on probabilities and uncertainties, taking into account the fact that the future is rarely deterministic. These models are ideal for environments where there are multiple possible outcomes, and the agent must weigh the likelihood of different scenarios. For instance, in a probabilistic model, an AI agent might need to decide between two possible actions, say taking route A or route B while driving. While route A may be shorter, there's a high chance that it will be congested based on real-time traffic data. Route B, on the other hand, is longer but has a lower probability of heavy traffic. The AI agent can use probabilistic reasoning to assess the likelihood of each scenario and choose the action with the highest expected outcome. This type of decision-making allows AI agents to act optimally in situations where certainty is not guaranteed, balancing risk and reward based on available data. The combination of these various decision-making models, rule-based systems, neural networks, and probabilistic models enables AI agents to tackle a wide range of decision-making tasks with varying degrees of complexity. In simpler scenarios, rule-based systems might be all that's needed, where the logic is clear-cut and the outcomes predictable. For more complex scenarios, where nuance, learning, and uncertainty are involved, neural networks and probabilistic models shine, allowing AI agents to make decisions that are not only informed, but also adaptive and probabilistically sound. However, decision-making in AI isn't just about selecting the best course of action based on data. It's also about optimizing that decision-making process. This is where reinforcement learning, a powerful subset of machine learning, takes decision-making to the next level. In reinforcement learning, AI agents are given goals or rewards and must learn through trial and error, adjusting their behavior based on the feedback they receive. This process is similar to how humans learn through experiences, where actions that lead to positive outcomes are reinforced and actions that lead to negative outcomes are discouraged. Reinforcement learning is particularly powerful in complex, dynamic environments where an AI agent must make decisions without explicit instructions, learning from its successes and failures. A common application of reinforcement learning is in robotics, where robots must learn to navigate complex environments, manipulate objects, or perform intricate tasks. For example, a robot learning to stack boxes in a warehouse would receive rewards when it successfully completes a task and penalties when it fails. Over time, the robot learns the most efficient strategies for stacking boxes, adjusting its actions based on the outcomes it experiences. This learning process allows the AI agent to optimize its decision-making abilities, continually refining its approach to achieve the highest level of performance. In real applications, decision-making algorithms are often used in combination to enhance the capabilities of AI agents. For example, an AI-powered drone used in delivery services might use a neural network for visual recognition of obstacles and a probabilistic model to assess weather conditions, combined with a rule-based system to ensure safe flight paths. In this scenario, the combination of decision-making models allows the drone to make real-time adjustments based on a variety of factors, ensuring both safety and efficiency in its operations. The real power of decision-making in AI agents lies in their ability to not only process information, but also to continuously improve and adapt over time. The feedback loops inherent in machine learning and reinforcement learning ensure that AI agents are always refining their strategies, learning from past decisions, and adjusting to new environments. This constant adaptation allows AI agents to operate effectively in dynamic, unpredictable situations, ensuring that their decision-making remains relevant and accurate as conditions change. Interaction with humans. The interaction between AI agents and humans is one of the most compelling aspects of artificial intelligence, bridging the gap between human intelligence and machine learning to create seamless, productive, and increasingly empathetic experiences. From the moment we pick up our smartphones to when we interact with chatbots on websites, AI agents are subtly embedded in our lives, helping us perform tasks, answer questions, and make decisions. These interactions are not just limited to simple command and response exchanges. They are evolving into complex dialogues that enhance the user experience and enrich our interactions with technology. The power of AI agents lies in their ability to interact with humans in a way that feels natural, intuitive, and increasingly personalized. One of the most well-known forms of this interaction is through virtual assistants like Siri, Alexa, or Google Assistant, which allow users to ask questions, set reminders, control smart devices, and access information all through voice commands. These AI agents are programmed to understand and process natural language, making them a gateway to a new kind of human-computer relationship, one that's conversational, adaptive, and constantly improving. At the core of human-AI interaction is natural language processing, NLP, which enables AI agents to understand human speech and text. NLP is a subfield of AI that focuses on the interaction between computers and humans using natural language, allowing AI agents to comprehend, interpret, and respond to the input they receive. This understanding isn't just about recognizing words, it's about grasping context, intent, and even the subtleties of human expression, such as humor, tone, and emotion. NLP allows AI agents to go beyond just regurgitating programmed responses and engage in more dynamic conversations with users. In many ways, virtual assistants are becoming extensions of our own capabilities. Instead of relying on traditional input methods like typing or searching, users can simply speak their requests, allowing for a faster, hands-free experience. A voice command to set a reminder, find the nearest coffee shop, or turn off the lights becomes a natural part of daily life. And the AI agent responds not only with efficiency, but with a degree of intelligence that continues to evolve. As these systems become more sophisticated, their ability to hold more contextually rich conversations, understand complex queries, and even detect emotional cues in a person's voice enhances the overall experience, making it feel more human-like. These interactions are not limited to personal assistants like Siri or Alexa, however. Chatbots in customer service are another area where AI agents play an integral role. These intelligent systems can engage with users through text-based communication, answering inquiries, solving problems, and guiding users through processes, all without the need for human intervention. From simple FAQs to more complex troubleshooting, chatbots are designed to offer instant support to customers, providing faster resolutions to issues and improving the overall efficiency of businesses. What sets these chatbots apart is their ability to continually learn from each conversation, adapting their responses over time to better meet the needs of the user. As businesses realize the importance of improving customer satisfaction, AI-driven interactions through chatbots are becoming a go-to solution for handling routine tasks that once required human agents. These systems can handle multiple interactions simultaneously, offer 24/7 availability, and even scale based on demand. But beyond simply answering questions, advanced chatbots powered by machine learning algorithms are capable of conducting multi-turn conversations, understanding context, and even addressing increasingly sophisticated customer needs. For example, a chatbot used by an e-commerce platform can assist customers in finding products, providing recommendations based on past purchases, checking order status, and offering personalized promotions, all through a single conversation. As these systems continue to evolve, they become capable of managing more complex queries, minimizing the need for human intervention, and improving the overall customer experience. The ability of AI agents to gather data from these interactions plays a critical role in refining the effectiveness of the system. Every time a user interacts with an AI agent, whether it's asking a question, requesting a task, or providing feedback, data is generated. This data can be used to improve the agent's understanding of individual preferences, behaviors, and needs, allowing the agent to personalize future interactions. For instance, an AI assistant in a smart home might learn your preferred room temperature, lighting, or music genre based on previous interactions, automatically adjusting settings to meet your preferences when you enter the room. Similarly, an AI-powered customer service bot can tailor its recommendations and responses based on previous inquiries or purchases, offering a level of personalization that was once reserved for in-person customer service. As these systems grow more sophisticated, the nature of human-AI interaction becomes more fluid, dynamic, and natural. Users begin to trust AI agents to handle more complex tasks, such as making travel arrangements, booking appointments, or even managing their finances. However, as AI agents increasingly take on these responsibilities, the way they interact with users must be both functional and empathetic. Understanding user emotions, tone, and context can transform a simple conversation into a meaningful and engaging experience. For instance, if a user expresses frustration with a service or issue, an AI agent can detect these emotions and adjust its responses to be more supportive, patient, and understanding. This level of emotional intelligence is crucial in building rapport with users, fostering trust, and enhancing the overall effectiveness of the interaction. AI agents are also becoming a pivotal part of healthcare, where their ability to interact with patients is changing the landscape of medical care. Virtual health assistants and AI-powered chatbots can engage with patients to provide basic health information, schedule appointments, and even monitor ongoing conditions. By using AI to understand patient needs, gather symptoms, and offer real-time support, these agents free up healthcare professionals to focus on more complex tasks, improving overall efficiency in the healthcare system. In telemedicine, AI agents serve as the initial point of contact, conducting preliminary assessments and ensuring that patients receive the appropriate care. These interactions can help address the global shortage of healthcare professionals and make healthcare more accessible, especially in underserved areas. In education, AI agents are providing personalized learning experiences that cater to the needs of individual students. Virtual tutors can interact with students, assess their understanding, and offer guidance tailored to their learning pace. These AI-driven tools have the potential to revolutionize education by offering one-on-one tutoring at scale, providing students with a tailored learning experience that adjusts in real time based on their progress. Whether it's answering questions, providing feedback, or offering additional resources, AI agents are transforming the educational landscape, making learning more accessible, efficient, and personalized. As AI continues to advance, the role of human-AI interaction is poised to grow, becoming a cornerstone of everyday life. The future of these interactions promises even more seamless integration into our lives, where AI agents will become trusted companions, enhancing productivity, simplifying tasks, and even enriching human experiences. For example, AI agents might work in concert with us in the workplace, handling routine administrative tasks, managing emails, or even assisting in complex decision-making processes. In the home, AI agents might anticipate our needs before we even express them, adjusting our environment, ordering groceries, or even offering reminders for important tasks. However, with these advancements come important ethical considerations. As AI agents interact with humans, they will increasingly have access to sensitive information, personal preferences, health data, financial information, and must be designed to respect privacy, uphold transparency, and function with a high degree of trustworthiness. Ensuring that AI systems operate within ethical guidelines and that users retain control over their data is paramount as these systems become more integrated into our daily lives. The interaction between AI agents and humans is transforming the way we live, work, and communicate. These intelligent systems are not simply tools. They are becoming collaborative partners, capable of understanding, adapting, and acting on our needs. From making our lives more convenient to solving complex problems, AI agents are enhancing our experiences in ways that were once the stuff of science fiction. As we look to the future, these interactions will only become more sophisticated, leading us into an era where technology and humanity work together seamlessly to build a smarter, more connected world. Environment adaptation. One of the most compelling and transformative abilities of AI agents lies in their capacity for environmental adaptation. This aspect of AI is particularly crucial as it allows agents to respond dynamically to changes in the environment, ensuring that they can perform effectively in ever-evolving and often unpredictable situations. The ability of AI agents to adapt to their environment goes beyond simply following predefined rules. It enables them to update their knowledge base, modify their actions, and adjust their strategies based on the real-time conditions they encounter. In essence, environment adaptation is what allows AI agents to not just react to their surroundings, but to learn from them, evolving over time to improve their performance and effectiveness. Imagine a self-driving car navigating through a busy city. The environment is constantly shifting, traffic patterns change, pedestrians cross the streets unpredictably, weather conditions fluctuate, and road obstacles appear out of nowhere. The AI agent within the car must continuously monitor all of these factors, assess the current state of the environment, and adapt its driving strategy accordingly. If the car encounters a sudden roadblock, it must analyze the situation, reassess its route, and take action, whether that means rerouting to avoid the blockage or adjusting speed to maintain safety. All of this must happen in real time. And the car's AI must adapt swiftly to ensure both the safety of the passengers and the efficiency of the journey. This capacity for adaptation is what sets AI agents apart from traditional systems. In the case of traditional automation, once a system is programmed to perform a specific task, it typically follows a rigid set of instructions, unable to adjust to unforeseen changes in the environment. AI agents, on the other hand, are capable of interpreting real-world data, modifying their behaviors, and even learning from their experiences. By doing so, they ensure that their actions are not only reactive, but proactive, improving their responses as they gain more exposure to different scenarios. A fundamental component of environment adaptation in AI is its ability to update its knowledge base. As AI agents interact with the world, they accumulate data and use this data to refine their understanding of the environment. This knowledge can range from simple facts, such as the optimal route between two locations, to more complex insights, such as how different weather conditions affect driving behavior, or how customer preferences evolve over time. With each new piece of information, the AI agent's knowledge base expands and becomes more accurate, allowing the agent to make better informed decisions in the future. Take the example of an AI-powered recommendation system in e-commerce. Initially, the system may have limited knowledge about a user's preferences, relying on basic demographic data or initial interactions. Over time, as the user continues to browse, search, and make purchases, the system collects more data, refining its understanding of the user's tastes and habits. With this new information, the AI agent adapts its recommendations to be more relevant, offering products that align with the user's evolving preferences. This dynamic learning process means that the system becomes more effective as it interacts with the user, continuously adjusting its actions based on the latest insights. This learning and adaptation process in AI agents is heavily influenced by the underlying algorithms that drive them. Machine learning, reinforcement learning, and other advanced AI techniques enable agents to identify patterns, recognize changes, and adjust their actions accordingly. For example, in reinforcement learning, an AI agent is trained to make decisions by interacting with an environment and receiving feedback in the form of rewards or penalties. The agent's goal is to maximize its rewards, and it learns by adjusting its strategies based on the outcomes of its actions. This type of learning enables the agent to adapt its behavior over time, continuously refining its approach to achieve better results. The ability of AI agents to adapt is also crucial in dynamic, real-time environments, such as supply chain management. In this context, AI agents are tasked with monitoring and optimizing various aspects of the supply chain, such as inventory levels, order fulfillment, and delivery scheduling. As the conditions change due to factors like fluctuations in demand, transportation delays, or supplier disruptions, the AI agent must assess the situation, update its knowledge base, and take action to maintain the efficiency and effectiveness of the system. For instance, if a key supplier fails to deliver on time, the AI agent may adapt by finding an alternative supplier, adjusting inventory levels, or rerouting shipments to meet the customer's needs. This ability to react to real-world disruptions and adapt in real time is a powerful tool for improving operational efficiency and resilience. Environment adaptation in AI also plays a significant role in robotics, where robots are tasked with performing complex, often unpredictable tasks in various environments. Consider a robot working in a warehouse, where its primary objective is to pick and place items. The robot must be able to navigate through crowded aisles, detect obstacles, and pick up objects of different shapes and sizes. Its environment is constantly changing. Boxes are moved, inventory levels fluctuate, and the layout of the warehouse can shift based on new shipments or changes in stock levels. The AI agent controlling the robot must adapt to these changes in real time, ensuring that it can continue to perform its tasks efficiently, despite the evolving environment. Over time, the robot's AI can learn new strategies, such as optimizing its path through the warehouse to minimize travel time, further enhancing its ability to adapt to its surroundings. One of the most exciting aspects of AI agents and their ability to adapt to the environment is their potential to improve the sustainability of various systems. For example, in smart cities, AI agents are used to optimize the use of resources like energy, water, and waste management. By gathering data from sensors throughout the city, such as traffic sensors, smart meters, and waste bins, the AI agents can monitor resource usage in real time and make adjustments to reduce waste, improve efficiency, and lower costs. If energy consumption spikes in a particular area, the AI can adjust the distribution of power, rerouting energy to meet demand, while minimizing environmental impact. Similarly, in waste management, AI agents can monitor the fullness of trash bins and optimize collection routes to minimize fuel consumption and reduce emissions. In agriculture, AI agents are increasingly being used to optimize crop management. These agents can monitor soil conditions, weather patterns, and plant health, adjusting irrigation schedules, pesticide use, and harvesting strategies accordingly. By continuously adapting to the changing environment, whether due to weather conditions, pest infestations, or soil depletion, the AI agents help farmers make more informed decisions, improving yields while minimizing environmental impact. This adaptability not only improves food security, but also contributes to more sustainable farming practices, ensuring that resources are used efficiently and that the impact on the environment is minimized. As AI agents continue to evolve and become more capable of adapting to their environments, the possibilities for their applications are vast. From healthcare to education, transportation to entertainment, the ability to learn from and respond to the environment allows AI agents to improve our lives in ways that were once unimaginable. They help optimize systems, streamline processes, and make real-time decisions that lead to better outcomes. However, with this power comes the responsibility to ensure that these agents operate ethically, transparently, and in ways that align with human values and goals. The future of AI agents is one where they seamlessly integrate into the fabric of our daily lives, continually adapting to new challenges and opportunities. Their ability to process information, learn from interactions, and adjust their behavior will drive innovation, improve efficiencies, and solve complex problems. As these agents become smarter, more flexible, and more autonomous, they will continue to enhance our world, making it more sustainable, efficient, and adaptable to the changes and challenges that lie ahead. In conclusion, the ability of AI agents to adapt to changes in their environment is one of their most defining and powerful characteristics. Through continuous learning, real-time decision-making, and the ability to update their knowledge base, AI agents are capable of navigating complex, dynamic systems and environments, from robotics and supply chains to smart cities and agriculture. The adaptability of AI agents enables them to optimize performance, respond to unforeseen challenges, and continuously improve over time. As AI technology continues to advance, the potential for these adaptive agents to transform industries, drive innovation, and create a more sustainable future is limitless, leading us into a world where machines work in harmony with humans to solve the challenges of today and tomorrow. Examples. The world of AI agents is vast and continually expanding, with applications that range from simple tasks to complex, autonomous systems capable of adapting, learning, and evolving in real time. Some of the most common examples of AI agents include chatbots, autonomous vehicles, personal assistants like Google Assistant, robots in manufacturing, recommendation systems, and virtual gaming characters. Each of these examples highlights the versatility of AI agents, showing how they are reshaping industries, enhancing our daily lives, and providing intelligent solutions to a wide range of problems. One of the most widely recognized examples of AI agents is chatbots, which have become a staple in customer service across industries. These AI agents are designed to simulate human conversations, providing instant responses to customer inquiries, offering product recommendations, and even solving problems. By processing natural language inputs from users, chatbots can engage in conversations that feel almost human, while leveraging large data sets to deliver the most accurate and relevant answers. Over time, chatbots learn from every interaction, improving their understanding of customer needs and refining their responses. This learning ability is powered by machine learning algorithms, which allow chatbots to adapt to new questions and evolve in response to changing customer expectations. Today, chatbots are not just used for basic customer service. They are increasingly deployed in more sophisticated scenarios, such as healthcare, where they can provide medical advice based on symptoms, or in finance, where they can guide users through complex transactions. Another powerful example of AI agents is autonomous vehicles, which represent a remarkable leap in AI's ability to perceive, analyze, and act in the real world. Autonomous vehicles, such as self-driving cars, rely on a combination of AI technologies, including computer vision, deep learning, and sensor fusion to navigate streets, avoid obstacles, and make split-second decisions. These vehicles are equipped with a variety of sensors, including cameras, radar, and LiDAR, which gather real-time data about the environment, such as road conditions, traffic patterns, and pedestrian movements. The AI agent processes this data, making decisions on how to drive, which routes to take, and how to avoid potential hazards. This level of decision-making requires not only the ability to process vast amounts of data, but also the capability to adapt to changing conditions, such as weather, traffic, or unexpected obstacles. Over time, autonomous vehicles learn from their experiences, improving their driving capabilities and becoming more efficient at navigating complex environments. These AI agents are a testament to the power of AI to transform industries, from transportation to logistics, and they hold the potential to revolutionize the way we travel and transport goods. Personal assistants like Google Assistant, Siri, and Alexa are other prime examples of AI agents that have become integral parts of our daily lives. These AI-powered assistants use natural language processing, NLP, to understand spoken commands and carry out tasks, such as setting reminders, sending messages, providing weather updates, or controlling smart devices in our homes. The technology behind these assistants is sophisticated, relying on large-scale data processing, speech recognition, and machine learning to understand the context of user commands and improve their responses over time. These personal assistants are designed to adapt to individual preferences, learning from user interactions to provide more personalized experiences. As users continue to interact with them, the assistants become more intuitive, anticipating needs and offering recommendations based on past behaviors. In addition to performing tasks, personal assistants are becoming increasingly capable of offering more complex, context-aware interactions, such as providing real-time traffic updates or answering questions based on the user's interests and location. And in the manufacturing industry, robots are another key example of AI agents that are transforming operations. These robots are designed to perform a wide range of tasks, from assembly line work to quality control, with incredible precision and efficiency. Powered by AI, these robots can adapt to changes in their environment, optimize their movements, and even learn new tasks over time. In the past, industrial robots were limited to performing simple, repetitive tasks that required little to no decision-making. Today, AI-driven robots are capable of much more, from performing complex assembly processes to adjusting their actions in real time based on sensor data. For example, in a factory setting, AI robots can analyze the shape and size of components, ensuring that each part is placed in the correct position, all while avoiding collisions with other objects in the workspace. These robots can even collaborate with human workers, creating a more efficient and flexible production environment. As AI technology continues to advance, these robots will become even more capable, with the potential to handle a broader range of tasks and improve the overall efficiency of manufacturing processes. Recommendation systems are yet another example of AI agents that play a significant role in shaping consumer behavior. These systems are ubiquitous in online retail, streaming services, and social media platforms where they help users discover products, content, and services that align with their preferences. By analyzing data from users' past interactions, such as purchases, clicks, or likes, recommendation systems learn to predict what items or content the user is likely to enjoy or find valuable. Over time, these systems refine their recommendations based on additional data, improving their accuracy and relevance. For example, in e-commerce, a recommendation system might suggest products based on a customer's previous purchases or browsing history. Similarly, on streaming platforms like Netflix or Spotify, the system suggests movies, shows, or music based on the user's preferences, creating a highly personalized experience. The more users interact with these systems, the more accurate the recommendations become, providing a tailored experience that drives engagement and increases sales or subscriptions. The success of recommendation systems is a direct result of the AI agent's ability to learn from user behavior and adapt its suggestions over time. Virtual gaming characters, or non-playable characters, NPCs, in video games represent another fascinating example of AI agents. In modern video games, NPCs are powered by AI algorithms that enable them to respond to player actions, interact with the game world, and even adapt to the player's behavior. These AI agents bring the game world to life, creating dynamic, immersive environments where players can engage in complex, unpredictable interactions. For example, in role-playing games, RPGs, NPCs can have conversations with players, react to the player's choices, and evolve based on the player's decisions. These characters are not simply following predefined scripts. They are actively learning from their interactions with players and adapting their behavior accordingly. This makes the gaming experience feel more organic and responsive, enhancing player engagement. As AI continues to advance, virtual gaming characters will become even more lifelike, capable of holding nuanced conversations and reacting to players in ways that are indistinguishable from human interactions. In each of these examples, AI agents are not just performing tasks. They are learning, adapting, and refining their actions over time to become more effective. whether they're providing customer support, driving a car, recommending products, manufacturing goods, or interacting with players in a game. These AI agents are designed to improve their performance based on the data they receive and the experiences they encounter. Their ability to learn from interactions, adapt to changes in their environment, and make decisions autonomously is what sets them apart from traditional systems, enabling them to handle more complex and dynamic tasks. The future of AI agents is incredibly promising, with new applications and capabilities emerging every day. As AI technology continues to evolve, we can expect even more sophisticated agents that can perform a wider range of tasks, interact with humans in more natural and meaningful ways, and continuously adapt to changing environments. From autonomous robots that work alongside humans in factories to AI-powered healthcare agents that assist doctors in diagnosing diseases, the potential for AI agents to improve our lives is limitless. Whether we're interacting with virtual assistants, playing video games, or navigating the roads in self-driving cars, AI agents are becoming an essential part of our daily lives, driving innovation, enhancing experiences, and solving problems in ways that were once unimaginable. In conclusion, AI agents are powerful, versatile, and continuously evolving entities that are already transforming industries and shaping the way we interact with technology. From chatbots and autonomous vehicles to personal assistants and gaming characters, these agents demonstrate the incredible potential of AI to enhance human capabilities, improve efficiency, and create personalized, meaningful experiences. As AI continues to evolve, we can expect even more exciting developments in this field, with AI agents becoming an even more integral part of our lives and society.